Strong acids are acids that completely break apart when they're added to water. They completely disassociate. The stronger an acid, the more hydrogen ions it releases. We know this because we know that the stronger an acid, it makes the pH go down. And when the pH goes down, it means that there are more hydrogen ions. But this word strong is specific to a type of acid that completely breaks apart in water. And there are 6 of them listed here: hydrochloric, nitric, hydriodic, perchloric, and chloric. But it's important to understand the difference between a strong acid and what we would call a stronger weak acid. So a weak acid does not ionize completely. It doesn't break apart. It's a weak electrolyte. A strong acid is 100% ionized. It is a strong electrolyte. Looking at the fat simulation, you can see here that in this case, we are looking at an acid. We can tell the pH is 4.5. The stronger we make the acid, the pH decreases. And that's because we have more hydronium ion concentration. So stronger acid, more hydronium ion. Weaker acid, it's not breaking apart as much. We still have quite a few of the HA, which stands for hydrogen plus some acid cation, that hasn't broken apart as much. Now, when I flip this right here, you can see that this now becomes what we call a strong acid. It is completely broken apart. The only way to decrease the pH of this is to increase the concentration. So if I increase the concentration, you'll notice there just happens to be more ions that show up there. And here's an example of electrolytes. There's a strong acid, definitely a strong electrolyte, whereas a weak acid is a weak electrolyte. The more dissociation that happens, the stronger electrolyte it becomes. So bases are pretty much the same as acids. As you can see here, a weak base has less dissociation than a stronger weak base. It turns from base into the hydroxide ions. The stronger the base, the more the hydroxide ions. The weaker the base, the less it's broken apart into those hydroxide ions. A strong base simply means that everything is broken apart and you have the maximum amount of hydroxide ions that can form. And again, the only way you can change the pH is by changing the concentration. Looking at a base as an electrolyte, it's the exact same thing. Strong bases, strong electrolytes. Weak bases, weaker electrolytes. This is that mom demo, and hopefully you'll get to see that or you've already seen it. Let's look here at a common reaction, okay? Hydrochloric acid is added to sodium hydroxide to produce NaCl and water. Hydrochloric acid is a strong acid, which means it will completely break apart in water. The hydrogen ions will completely break apart from the chlorine ions. Sodium hydroxide is a strong base. The hydroxide ions, or OH, will completely break away from the Na+. What they result in is sodium chloride in water. So again, hydrochloric acid plus sodium hydroxide equals NaCl, which we know is table salt, and water. Take a look at this again. It's actually a double replacement reaction. I want to show you HCl gets together with NaOH. Do-si-do, the Na bonds to the Cl, and the OH bonds to the H. So it results in sodium chloride and hydrogen hydroxide, or water. So every time an acid is added to a base, it results in a salt and water, and that happens because of that double replacement reaction. Putting a base into an acid is going to bring the pH up. The base's hydroxide ions combine with the acid's hydrogen ions to make water. Again, in this chapter only, I want you to think about water not as H2O, but instead of H2O as hydrogen hydroxide, HOH. And that kind of reminds you that it's when an H plus and an OH minus get together. Putting an acid into a base brings the pH down. The acids H plus combine with the bases OH to make water. So an acid plus a base equals a salt in water. When I say salt in chemistry, it's not the same thing as when I say salt in the kitchen. Salt in the kitchen is NaCl, but a salt in chemistry is a chemical compound formed by ionic bonds between cations and anions. A salt is very specifically something that's made in an acid-base reaction. So next time you hear the word salt in chemistry, don't think that it always has to be NaCl. This is kind of a silly little comic that sometimes you'll see. The base is under a salt, and then you'll see written NaCl, NaOH. See? The base is under a salt. Here's another neutralization reaction shown. Acid plus base equals salt plus water. Same thing as we were talking about, but a different acid and a different base. This is what we call nitric acid, a hydrogen and a nitrate ion. And this base is potassium hydroxide. So again, do-si-do, hydrogen gets with hydroxide to produce water, and the potassium gets with the NO3 or nitrate to produce salt or potassium nitrate. So the acid in the equation is nitric acid. It produces the H plus ions. The base is the potassium hydroxide. It produces the OH ions. And then the salt is that ionic compound that's the product of a neutralization reaction. What we can use neutralization reactions for is something called titration. In chemistry, titration is used to determine the concentration of an unknown solution. This is how it works. Basically, you have some unknown solution. It might be an acid, it might be a base. It's an unknown acid or base concentration. Into that, we're going to add some known solution. So if this is an acid, we're going to add a known solution of a base. The way that we then calculate is we determine the moles of the known solution that we add until this right here reaches neutral. Then you use stoichiometry to find the moles of the unknown. Find the molarity of the unknown because you know the moles and the liters used. So again, in this kind of example, it says drop the base. Let's pretend that down here we have some acid, okay? Let's go with nice and simple. We have hydrochloric acid, and we don't know what the molarity is of that hydrochloric acid. Up here, we're going to have a known solution of a base. So we're going to have NaOH, for example. And let's just say this is 2 molar. Then what will happen is the person slowly adds it to here. In order to find out if this is neutralized, you're either going to use a pH meter, indicator, or what we like to use a lot is phenolphthalein. And you saw this one before. So phenolphthalein in this case is going to start out clear if we're dropping the base. And then as we drop it, it's going to start to turn pink. If you reverse this and you add the acid to the base, you're going to get the opposite because phenolphthalein is clear in an acid and pink in a base. We're going to see here how a titration looks in real life. The scientist is adding phenolphthalein indicator And we can see that this one is going to run the opposite way that I was just talking about. This is a base, and we know that because it turns pink. The scientist is going to make sure to keep things swirling the entire time. Place the flask underneath the burette and start to add the acid into the base. Now, the first trial is sometimes done rather quickly. This is sort of a throwaway trial because you're just getting an idea to figure out about how much acid you need to add until you reach neutralization. After you look at how the burette has moved, you can calculate how much you should use approximately for your next trial. For your second trial, you're going to be a lot more careful. You're going to add it slowly. Pay attention to exactly how far the burette moves. Make your measurements more accurate. Continue to spin the flask the entire time. Sometimes it's easy to put a white piece of paper under so you can see the color change even better. Because as you add, in this case, the acid into the base, the color is going to start to disappear. If we were going in the opposite direction, we would be looking for colors starting to form. Notice at the end, the scientist is going one drop at a time. This one drop at a time method is going to make sure that we reach the exact point of neutralization or the exact end point. Then you can work on the math. So let's go through an example. 42.5 milliliters of 1.3 potassium hydroxide are required to neutralize 50 milliliters of sulfuric acid. Find the molarity of sulfuric acid. So the first thing we're going to need is a balanced chemical formula. Here it is. So we can use stoichiometry. Let's start out with what we know. Now I converted this right away into liters. I moved the decimal point over and I said, well, I know that this is 0.0425 liters. I'm not sure why I wrote milliliters there. That's actually wrong. This is liters. You can do this conversion in the dimensional analysis, but sometimes it's just easier to do it by hand. Then we know that that has a molarity of 1.3 moles per liter. That's molarity. Remember, M is molarity or moles over liters. That's why I needed to convert that to liters first. This is going to cancel. Liters will cancel. Now you're in moles. Well, we know that we are neutralizing 50 liters of it. So you can put this before or after, but you know that you're going to want your end result in a molarity. And molarity is going to be moles over liters. So that's why I put the liters used of the H2SO4 on the bottom. Now, where did this come from? This is that magic step in stoichiometry. I told you, stoichiometry was never, ever, ever going to go away. This step is the step that's in every stoichiometry problem. This step says for every 1 mole of H2SO4, there are 2 moles of KOH. So we know that because it's going to have a 2-to-1 ratio in the acid and the base, but this is how we put it into the stoichiometry problem. So after everything cancels, you're left in moles per liter of H2SO4, and another word for that is molarity. Now let's just say you're really over stoichiometry and you have no interest in ever learning stoichiometry ever again. Don't get upset. There is a way to cheat this without stoichiometry. The way that we do that is it's moles of hydronium ion equal moles of hydroxide ions. And here's the formula. Molarity of the acid, volume of the acid, number of H ions of the acid. molarity of the base, volume of the base, number of OH ions for the base. So the trickiest part to this is using that N. So HCl has an N value of 1 because there's just one hydrogen. H2SO4 has an N value of 2. Okay? So this is counting your number of hydrogens in your acid. The base, same thing. NaOH has an N value of 1. MgOH2 has an N value of 2. In the base, you're counting hydroxide. So when you use the formula, it's just plug and chug. You've got 42.5 milliliters, and notice you can leave this in milliliters. The molarity of the base is 1.3 molar. The N of the base is just 1. KOH has 1 hydroxide ion. The acid that we're going to add is H2SO4, so N for the acid is going to equal 2. And then you know your volume of your acid added. Again, as long as these are the same unit, that's fine. And then you'll plug and chug to get your molarity of your acid. So here's X, solve for X. Reminder to those of you who have forgotten some algebra, divide by 50, divide by 2. Those are going to cancel, divide by 50. Also divide by 2, and you're going to get your answer of a molarity of 0.55 molar H2SO4, which is sulfuric acid.